Welcome back. So today we're going to talk about chapter 5 and chapter 10. So chapter 5 has to do with Z-scoring, raw score data, and chapter 10 has to do with calculating correlation and regression, which has to do with the relationship between two variables. So before we begin, let me review a couple important concepts. Okay, so I always like to begin talking about the two types of statistics. Okay, so what are the two types of statistics? The first type is descriptive, okay? And then there are two types of descriptive statistics. Okay, so there's central tendency and variability. So those are the two types of descriptive statistics. And you know, when we went over chapter 3, which was central tendency, we talked about the mean, we talked about the median, which is also known as the Q2 or the 50th percentile. We talked about the mode. But in here we also talked about the Q1, or the 25th percentile, and the Q3, or the 75th percentile. And there's some other things we talked about there as well, and everything came together in the box plot. Okay, so variability, which was chapter 4, we talked about range, which is the maximum value minus the minimum value, and it's the range of 100% of the distribution of data. We talked about IQR, which is the interquartile range, and IQR is the Q3 minus the Q1, and it gives you the range of the middle 50% of the data. And if you don't remember that, go ahead and go back to, I believe I explained it actually in the chapter 3 and the chapter 4 video, but it's that idea when you draw out your box plot, 25% of the data is contained between the minimum and the Q1, another 25 between the Q1 and the Q2, another 25 between the Q2 and the Q3, and the last 25 between the Q3 and the maximum. Okay, and lastly, we talked about the standard deviation. Okay, so above and beyond central tendency and variability, we talked about frequency. So frequency is simply, organizing and displaying the numbers. And by organizing the numbers, you can kind of figure out central tendency, which is the most typical value in a distribution of data. And you can also figure out variability, which has to do with spread. But in frequency, we talked about simple frequency, we talked about grouped frequency, we talked about frequency polygon and histogram, we talked about the bar chart, or the bar graph, and we talked about relative frequency. Okay, so what we covered so far are basically descriptive statistics for one variable of data at a time. So that's known as univariate. I'll write that down. So essentially everything we've done so far, all this, is univariate. Or we could call it univariate descriptive statistics. So what we're going to learn about today is a concept related to the standard deviation, okay? And that concept is Z-score. So I'll draw an arrow and bring it out over here. And Z-score is still univariate, right? Because you do it on one variable at a time, okay? We'll go over what that looks like. But something else we're going to do today that I'm going to call it a bivariate descriptive statistics, is we're going to do correlation and regression. I think that's a good way of thinking about it. And the reason why I'm calling it a bivariate descriptive statistics is correlation and regression are describing the relationship between two variables. We haven't done anything like that yet. We have just dealt with one variable at a time. Okay, so as you can see in our little diagram over here, you've learned a lot so far, okay? But we're going to take it a step further next week, okay? And we're going to talk about inferential statistics. So I'm going to add that over here, inferential statistics. That is the second type of statistics. And in inferential statistics, you're simply doing this. You're trying to make a statement about the greater population based on a sample that you have. Okay? Okay, so that's where we've been so far. So we're going to get into the concept of Z-score and correlation and regression today, and then the week after we're going to push into inferential statistics. Okay, let me go ahead and erase the board, and then I will continue. Okay, so let's talk about the data that we're going to be dealing with today. So if you have my lecture notes open, you'll see that I have the data in two columns, right? One for X, which is satisfaction with life, and one for Y, which is self-esteem. Unfortunately, because my whiteboard isn't that long, I have to split it into two columns. So let me just get you acquainted with what's going on the board. So X, which is in black, is satisfaction with life. Okay? So satisfaction with life scores, satisfaction with life scores. You're going to notice in red next to the scores, you'll see S1, S2, S3, etc., all the way down to S26. S stands for subject, or you can think of it as participant. So it just means it's an individual. In blue, you have self-esteem, okay? Self-esteem, self-esteem continued. Okay, so one thing I want you to notice here is for subject 1, they have a satisfaction with life score of 1.8 and a self-esteem score of 2.7. Okay? Participant 19 has a satisfaction with life score of 5.2 and a self-esteem score of 3. Okay, so it's important that you don't mix up the data because we're calculating the relationship between these two variables. Therefore, we need to keep the data related, right, by participant. You want to have participant 1's satisfaction with life score and their self-esteem score. You don't want to mix participant 1's satisfaction with life score and participant 15's self-esteem score. It would be completely meaningless, right? So one thing I want to point out regarding satisfaction with life, the lowest satisfaction with life score is 1, the highest is 7, okay? And the higher the satisfaction with life's value or score, the higher someone's satisfaction with life. For self-esteem, the lowest possible score is 1, and the highest possible score is 4. Okay? Higher scores mean higher self-esteem. Okay. So the first thing we want to do when we're dealing with finding the relationship between two variables is we want to create something called a scatter plot. And you've all probably heard of this before. So to make a scatter plot, you draw a simple XY plane. And then you have to figure out which one you want on the y-axis, which one you want on the x-axis. So in this case, I tell you, right? Because I'm telling you x is satisfaction with life and y is self-esteem. So this is going to matter when we talk about regression, but we'll cross that bridge when we get there. So the y-axis is self-esteem, the x-axis is satisfaction with life. Okay. So the highest possible self-esteem score is a 4. So we'll count it out. 1, 2, 3, 4, something like that. Okay. The highest possible satisfaction with life score is a 7. 1, 2, 3, 4, 5. Six, 7. So technically, we could get rid of the 0 point by bumping everything over 1, right? So this could be 1 and this could be 1, but this is fine because technically 0 isn't a possibility. But we'll go with this. This is gonna work. Okay, so now all we have to do is we have to plot the points that we're given, right? So for subject 1, they have an x of 1.8 and a y of 2.7. So an x of 1.8 and a y of 2.7. Okay. So I'm just going to plot all these points. Subject 2 is 2 and 2. Subject 3 is 2 and 1.9, which is basically the same. Subject 4 is 2.8 and 3.9. Subject 5 is 3.4 and 2.9. Subject 6 is 3.4 and 2.8, which is about the same. Subject 7 is 3.4 and 3.2. So a little higher. Subject 8 is 3.4 and 3. Subject 9 is 4 and 2.7. Somewhere like there. Subject 10 is 4.4 and 3.8. 4.4 and 3.8, somewhere around there. Subject 11 is 4.6 and 3.1. Subject 12 is 4.6 and 3.9. Subject 13 is 4.8 and 3.8. 14 is 4.8 and 3.7. 15 is 5.2 and 3.3. Somewhere like there, you know. 16 is 5.2 and 3.9. It's a little higher. 17 is 5.2 and 2.9. 18 is 5.2 and 3.1. 19 is 5.2 and 3. 20 is 5.2 and 3.1. 21 is 5.4 and 3.8. 22 is 5.8 and 3.3. 23 is 6 and 4. 24 is 6 and 2.9. 25 is 6 and 3.2. 26 is 6.4 and 4. Okay, there you have it. And that's a pretty good picture. What do you notice is the relationship between these variables? Well, what's going on? Well, it looks like, right, high scores in self-esteem tend to be associated with high scores in satisfaction with life, and vice versa, right? So let me give myself a little more space. I don't have much space to work with here. Let's go ahead and erase the word scatter plot. So when we're talking about correlation, we need to talk about two things. We need to talk about direction, and we need to talk about size of the correlation. So the first thing we're going to talk about is direction. Okay. The first I'm going to show you is a positive correlation. So in a positive correlation, the dots are trending from the lower left, okay, to the upper right. Okay. So obviously, that's what our scatter plot here looks like. Now I'm going to show you a negative correlation. So a negative correlation is opposite, as you can see. So here you have the dots trending or starting in the upper left and working their way down to the lower right. So our dots are not doing that, so we don't have a negative correlation. The last one I'm going to show you is no correlation or no relationship. And if there's no relationship, you're just going to see a bunch of dots everywhere. Okay? A bunch of dots everywhere. Okay, I think that's good. So we talked about direction. Let's talk about size of the correlation, or what it's often called is magnitude. Okay, the highest possible positive correlation is going to be +1. Okay, R equals +1. Or usually just R equals 1. Okay, the plus is implied. So what is that going to look like? The dots are going to be pretty much in a straight line. Okay? Now let's do R equals, let's say, a +0.5. You're going to see the dots spreading out. Okay. Now look at R +0.2. You're going to see the dots spreading out even more, but it's still like trending in the positive direction. Okay, maybe that's a little too much. Let's get rid of some of that spread, and let's get rid of some of the spread here, just to really illustrate the point. Okay, and then if we get to R equals 0, R equals 0 means no relationship. Then that's where we have this, the points just like everywhere. Okay? Okay, so for review, the largest possible positive correlation is a +1. Okay? And notice how the dots are on this imaginary line here. Okay, and then let's drop it down. R equals +0.5. Okay, it's probably something like this. So the dots are spreading away from that imaginary line, right? Because it's not as strong or large of a relationship between the two variables. 0.2 is spreading even more, okay? And then 0 is no relationship, so it's, the dots are just everywhere. Okay. So now we could do the same thing, but now we can talk about the largest negative relationship. So 0, if you notice, I didn't erase 0 because you're not going to have a positive 0 or a negative 0. 0, 0, it means no relationship. So a perfect negative relationship is -1. So notice how the line is just slanted in the opposite direction. And it's going to be on an imaginary line that's pretty straight. It's 0.5, again, it's going to deviate from that imaginary line. 0.2, it's going to deviate even more. Okay, let me add my negatives here. Okay, so R equals -1, a perfect negative relationship. All these dots are on this imaginary line right there. Okay, then you have R equals -0.5. Okay, the dots are spreading out. Then you have R equals -0.2, the dots are spreading out even more, and then of course R equals 0, which is no relationship. They're just like randomly placed. Okay, so I feel good about that. We covered size and direction. So one thing we could do with the scatter plot, but it's not really necessary, is we can look at the scatter plot and kind of predict the relationship between the two variables. So obviously, based on what we learned about direction, this is a positive correlation. It's definitely not a +1, right? It's not a perfect positive correlation. You know, it could be like a 0.5. R equals 0.5. That seems reasonable because it's not as spread out as like the 0.2. Okay? So what I'm going to do right now is I'm going to erase the scatter plot as well as the the size that I have up there, and then we're going to go ahead and we're going to start talking about Z-score. Okay, so the next thing we're going to talk about is Z-score. So the equation for Z-score is x minus the mean divided by the standard deviation. Okay, so let's go ahead and do that. So we're going to do that for the x distribution as well as the y distribution. So you might be thinking, wait, but we haven't calculated the mean and we don't have the standard deviation. Well, that's okay, because I'm going to give it to us. Okay, so the mean for the satisfaction with life distribution is going to be 4.47, and the standard deviation is going to be 1.32. And again, I'm color coding it, right? Satisfaction with life is black. And for self-esteem, the mean is going to be 3.23, and the standard deviation is going to be 0.58. Okay, I think we're in business there. So the best way to do this is just add columns. So we're going to have a column that's going to be x minus the mean, right? And then x minus the mean divided by the standard deviation. Okay. So we'll just add it here. X minus the mean. X minus the mean divided by the standard deviation. And we'll do the same thing over here. Y minus the mean. Y minus the mean divided by the standard deviation. Y minus the mean. Y minus the mean divided by the standard deviation. So this is actually in the way. I'm going to erase this. Okay, perfect. Okay, so let's just start doing it. That's how we're going to get done. So it's going to be 1.8 minus 4.47. Okay, so you should get negative 2.67. Okay, and then you have 2 minus 4.47. Right? And you should get negative 2.47. Okay, so now just keep on doing that. And I'll write up the answers. Okay, 4.8 minus 4.47 is 0.33. 5.2 minus 4.47 is 0.73. There's a bunch of those. .2 minus 4.4, oh, we're still there. There's a bunch of those. Thought it was done. 5.4 minus 4.47 is going to be 0.93. 5.8 minus 4.47 is going to be 1.33. 6 minus 4.47 is going to be 1.53. And 6.4 minus 4.47 is going to be 1.93. So let me just make sure I got them all correct. Yeah, looks good. So what you might be thinking to yourself is, hey, I think we've done this before. Yeah, and we have done it before, right? Because we had to get the deviation scores, because that's what these are, in order to calculate the standard deviation. And we did that in chapter 4. So you've done this procedure before. So what you haven't done before is you haven't taken the deviation score and divided it by the standard deviation. So let's go ahead and do that. Okay. So negative 2.67 divided by the standard deviation, which is 1.32, is going to give you negative 2.02. And if this is a little small, feel free to go to Files. What week are we in? Week 3, by hand, lecture, and the notes are right there. So, and that's what I'm looking at. So go ahead and do that. Negative 2.47 divided by the standard deviation is negative 1.87. So there's a few of those. Okay. So just keep on doing that. I'm going to write up some of the answers and then I'll pick it up again. Okay, 0.33 divided by the standard deviation is 0.25. So we have a couple of those. 0.73 divided by the standard deviation is 0.55. Point 93 divided by the standard deviation is going to be 0.70. 1.33 divided by the standard deviation is 1.01. 1.53 divided by the standard deviation is 1.16. Okay. And then the last one, 1.93 divided by the standard deviation is 1.46. And these are all z-scores. So when you get to the stage where you've done the deviation score and you divide by the standard deviation, what you're left with is the z-score. So now we can do the same thing for the y distribution, or rather the self-esteem distribution. So let's go ahead and do that. So we have 2.7 minus the mean, which is 3.23, and we're going to get negative 0.53. 2 minus 3.23, negative 1.23. 1.9 minus 3.23, we get a negative 1.33. So I'm going to go ahead and write a few, and then I'm going to pick it back up again. Yeah, so what I continuously do here, and you're probably noticing it, is I'm checking the numbers. There's a You know, the math isn't hard, but there's a lot going on. So if you make one mistake, you'll just blow up the entire problem. So you just want to be really vigilant. Okay, so 3.8 minus 3.23, we're going to get 0.57. 3.7 minus 3.23, we're going to get 0.47. 3.3 minus 3.23, 0.07. 3.9 minus 3.23, we're going to get 0.67. 2.9 minus 3.23, we're going to get negative 0.33. 3.1 minus 3.23, we're going to get negative 0.13. 3 minus 3.23, we're going to get negative 0.23. 3.1 minus 3.23, minus 0.13. 3.8 minus 3.23, 0.57. 3.3 minus 3.23, 0.07. 4 minus 3.23, we're going to get 0.77. 2.9 minus 3.23, we're going to get negative 0.33. 3.4 minus 3.23, we're going to get 0.17. 4 minus 3.23, we're going to get 0.77. Okay, again, let me go ahead and check those. Really easy to make a mistake here. Super duper easy. Okay, great. So again, we calculated the deviation scores for the self-esteem distribution. So now, according to the z-score equation, we need to go ahead and divide by the standard deviation in order to get our z-scores. So let's go ahead and do that. The standard deviation is 0.58. So negative 0.53 divided by 0.58 is a negative 0.91. Negative 1.23 divided by 0.58 is negative 2.12. Negative 1.33 divided by 5.8 is a negative 2.29. Okay, so I'm gonna do a few and then I'm gonna pick it up again. Let's go. 0.67 divided by 0.58 is 1. 0.16. Okay, let's go to 0.67 divided by 0.58. We're going to get 1.16. Negative 0.33 divided by 0.58. We're going to get negative 0.57. Negative 0.13 divided by 0.58. We're going to get negative 0.22. Negative 0.23 divided by 0.58. We're going to get negative 0.40. Negative 0.13 divided by 0.58, we're going to get negative 0.22. 0.57 divided by 0.58, we're going to get 0.98. 0.07 divided by 0.58, we're going to get 0.12. 0.77 divided by 0.58, we're going to get 1.33. Negative 0.33 divided by 0.58, we're going to get negative 0.57. 0.17 divided by 0.58, we're going to get 0.29. 0.77 divided by 0.58, we're going to get 1.33. I'm going to go ahead and check these, and then we can move on. So let's see. Okay, good. Let's talk about z-scores for a little bit. And then we'll go ahead and calculate the correlation. We're almost there. It's really not too difficult from this point. Okay, so z-scores have something in common with a deviation score. Okay, and that's the first thing. Let's look at the z-scores for the satisfaction with life distribution of data. Okay, we have, for subject 1, we have a negative 2.02. Because it's negative, it means that their score is below the mean of the distribution of data. And here's where we get that. Okay, the numerator of the z-score equation is x minus the mean. That is the same as the deviation score. So when we were working with deviation scores, I told you the same thing. So let's make a list of what we're learning right here. Okay, so what can you do with z-scores? So z-scores. The first thing you could do is you can compare Sorry, I need to get my eraser. I just made a mess. Okay. So I'm going to start using some lingo that's important. You can compare raw scores in a distribution of data to each other. That sounds pretty good. Okay, so what do I mean? Well, your x here means raw score. Your x and y means raw score. Your zx and your zy would be your z scores, okay, or your transformed raw scores. Okay, so subject 1 has a raw score of satisfaction with life of 1.8, and the corresponding z-score is a negative 2.02. So what is that telling you when we compare this z-score to the other z-scores? It's telling you that a 1.8 is going to be below the average satisfaction with life score for this distribution of data. Specifically, how we interpret this, I'm just going to put a for example here and stick in the interpretation for a z-score. Essentially, when we say subject 1 has a z-score of negative 2.02, we're saying I'll write it out and then I'll tell you. Okay, so subject 1's raw score is 1.8 and their z-score is negative 2.02. So what that means and how you can interpret that z-score is you could say subject 1's raw score of 1.8 is 2.02 standard deviation units below the mean. Okay, so below the mean comes from the fact that it's a negative number. Otherwise, it would be above the mean. Okay, and the reason why we say standard deviation units is because we're taking that deviation score and we're dividing by the standard deviation. That's what gets us that interpretation. So again, the only thing that would change, let's say their z-score was a positive 2.02, then we would say subject 1's raw score of blank is 2.02 standard deviation units above the mean. Okay, that's good. I'm happy with that. I'm going to erase this because I need some board space. The second cool thing we could do with z-scores is we can compare between distributions of data. Well, that means we can compare someone's satisfaction with life score to their self-esteem score. And that makes sense, but you could also do stupid stuff, like you could compare someone's satisfaction with life score to their exam score, or the place they finished in the race, stuff like that. When you z-score two distributions of data, you could just compare anything. Okay, so let me show you what that looks like though. Okay. Great. So let's just stay with subject 1. So subject 1 has a z-score for satisfaction with life of negative 2.02. Okay? And they have a z-score of negative 0.91 for self-esteem. I'll write it down. Subject 1, z satisfaction is going to be negative 2.02. I'm going to get a new marker. Alright, that's a lot better. Okay, and then subject 1, z for self-esteem is going to be negative 0.91. So again, the interpretation for subject 1's z-score for satisfaction with life is subject 1's raw score of 1.8 is 2.02 standard deviation units below the mean. Okay? Now let's do their interpretation for self-esteem. Subject 1's raw score for self-esteem is 2.7, and that is negative 0.91 standard deviation units below the mean. Okay. So what we can do here is we can compare the z-scores. So the question we can ask ourselves, does subject 1 have a better satisfaction with life, okay, or a better self-esteem? Well, remember, negative numbers can trip us up here. Remember the concept of a number line? We have 0, +1, +2, etc. 0, negative 1, negative 2. Okay. So 0 is going to be below the mean, right? So subject 1 satisfaction with life is right over here. So it's negative 2.02 standard deviation units below the mean, but their self-esteem score is only negative 0.91 standard deviation units below the mean. Therefore, even though both are below the mean, which isn't good, subject 1 has a greater self-esteem than they do satisfaction with life. Let me give you one more example, just demonstrating how this can be tricky. Let me find a good one here. Okay, let's look at subject 23. That's a good one. So subject 23 has a Z-score for satisfaction with life of 1.16. And they have a Z-score for self-esteem of 1.33. So here's the thing. Taking it at face value, we're going to see that their satisfaction with life score is a 6, okay? And their self-esteem score is a 4. So just by looking at the raw scores, you would say to yourself logically, well, participant 23 has a raw score of 6, and sorry, I'm gonna start that over. Participant 23 has a raw satisfaction with life score of 6 and a raw self-esteem score of 4. So you would think, well, their satisfaction with life is higher than their self-esteem. But that's not the case. You cannot compare the distributions unless you Z-score them. Okay? And by Z-scoring them, we're looking at the score compared to the average of the distribution and dividing by the standard deviation, which then puts that number in context. Okay, so let's go ahead and draw out our number line. Okay, we have 0, negative 1, negative 2, plus 1, plus 2. Okay, so subject 23 has a satisfaction with life score of 1.16 and a self-esteem score of 1.33. So when we look at these raw scores in the context of the average and the standard deviation for each distribution, it turns out that participant 23's self-esteem score is actually slightly higher than their satisfaction with life score. Even though the raw scores may lead you to think the opposite. I'm going to give you one more example here that I think resonates really well with students. So take a look. I'm just going to erase these two little examples and I'm going to put more on the board. Let's do it. And this is actually something that happened a lot when I was going to school. Okay, so let's say it is midterms, or even better, it's finals. And your friend reports to you that they got a 50% on their biology exam. And you tell them, well, I got an 80% on my psychology exam. And to yourself, you're thinking that you did better than they did. Nah, that's actually incorrect reasoning, because you haven't taken into account the average of the biology distribution of test scores and the standard deviation, and you haven't done the same for the psychology distribution. So let's take a look at it. Let's add some context. Now, what if I tell you that the average on the biology exam was a 20 and the standard deviation was 10? The average on the psychology exam was 90 and the standard deviation was 10. So let's go ahead and calculate those. So 50 minus 20 is 30, right? Divided by 10, biology is going to have a z-score of +3, and then psychology, 80 minus 90 is going to be -10 divided by 10 is going to be a z-score of -1. So you scored -1 standard deviation units below the average for the psychology exam distribution, and your friend scored 3 standard deviation units above the average of the biology distribution of data. So it turns out that you actually did worse on your psychology exam than they did on their biology exam. The last thing I want to talk about regarding z-scores is you can use z-scores to find outliers in your data. So basically, the rule is any raw scores that have a z-score of +3 or higher, -3 or lower, are going to be considered outliers. So +3 or higher will be considered outliers. -3 or lower will be considered outliers. Okay, so let's go ahead and check it out. So literally what we can do right now is we can look at all our z-scores and see if any of them qualify. So -2, -1, -1, -point, okay. So I'm looking through all the z-scores, seeing if any of them qualify. And in fact, we don't have any z-scores that are +3 or higher or -3 or lower. Therefore, we don't have any outliers. But let's say we had a z-score of +3, 1. Well, that raw score would be an outlier in the distribution of data. So this is another way to identify z-scores, and we're going to be going over this in our SPSS lecture next week. It's super easy to implement this method in SPSS. A lot easier than the other interquartile range definition that we previously learned about. Okay, so those are the three things you could do with z-scores. So go ahead and take a look at that. I'm going to go ahead and erase it. Okay, so now we're going to figure out how to calculate R. R equals the sum of Zx multiplied by Zy divided by n. So that's our equation. Okay, so Zx multiplied by Zy is the next thing that we have to do. So every participant has a Zx or a Z-score for their satisfaction with life raw score. And they also have a Z-score for Y, or rather their Z-score for their self-esteem raw score. So let's take a look at that. What I'm going to do is I'm going to make a new column. So subject 1, subject 2, subject 3, all the way to 26. And what you're going to do is you're going to multiply the z-scores. So I'll circle them and then indicate the answer. Okay, so subject 1 had a satisfaction with life z-score of negative 2.02, and they had a self-esteem z-score of negative 0.91. So it turns out that when you multiply the two, you get 1.85. Okay, subject 2 has a satisfaction with life z-score of negative 1.87, and they have a self-esteem z-score of negative 2.12. When you multiply those two, you get 3.97. Subject 3 has a z-score for satisfaction with life of negative 1.87, for self-esteem negative 2.29. If you multiply those together, you get 4.29. So what I'm going to do is I'm going to go ahead and I'm going to keep on going, and I'll pick it up towards the end. So just keep on multiplying the z-scores together per subject. Okay, so subject 21.7 multiplied by 0.98, 0.69, 22 is 1.01 multiplied by 0.12. It's going to give us about 0.12. Subject 23, 1.16 multiplied by 1.33. It's going to give us 1.54. Subject 24, 1.16 multiplied by negative 0.57. It's going to give us negative 0.66. 1.16 multiplied by 0.29 is going to give us 0.34. 1.46 multiplied by 1.33 should give us 1.94. So I'm going to go ahead and check these, and then we're going to keep on going. Okay, that looks good. So the next step is going to be this. So we multiplied the zx and the zy's together for each subject. So now we just have to sum that or add them together. So now you're just going to add up all of these values. So go ahead and add up all of the values, and you should get You should get 14.78. So after you add up all the values and you get 14.78, you could plug that 14.78 into the top part of the equation. And then all that's left for you to do is to divide by the n. Okay? Well, what's the sample size in this case? Is it, well, we have 26 satisfaction with life scores, and we have 26 self-esteem scores. So is our sample size 52? No, think of it as n pairs. How many pairs of scores do we have? You can think of it that way, or think of it, how many participants do we have? Well, we have 26 participants. So that's exactly what n is going to be. So then 14.78 divided by 26 will give you R equals 0.57. Okay. That was the hard part. So make sure you have all this. What I'm going to do now is I'm going to erase what we just did, and I'm going to write the interpretation, okay, for the correlation. You know what? I could actually, at this point, I can go ahead and delete the data. But before I do that, look at everything you just did. Praise God. It's amazing. Congratulations. So let me erase this beautiful board real quick. see. Okay, so we determined R is 0.57, okay? So I usually write 3 dots. So 3 dots means therefore. Okay, so the first thing you're going to say, therefore, there is a very large positive relationship between satisfaction with life and self-esteem. Okay, cool. So, what are the moving parts here? Very large has to do with the size or the magnitude, and positive has to do with the direction. So your options are this. If it's a negative correlation, right, so R equals negative 0.57, for example, then it would be negative. But because R equals 0.57, or the implied plus 0.57, we're saying it's a positive relationship. Now, how do we determine size? Well, there's some standard cutoffs. 0.1 is considered a small correlation. 0.3 is a medium correlation, and 0.5 is a large correlation. So these are the guidelines, right? So if it's less than 0.1, you can say very small. If it's exactly 0.1, you can say small. If it's between, and by the way, this is all plus or minus, so let me add that. Plus or minus, right? Because this has to do with size, it doesn't really care about direction. So if the correlation's between 0.1 and 0.3, you can say there's a small to medium relationship. If it's about 0.3, you can say there's a medium relationship. If it's between 0.3 and 0.5, you can say there's a medium to large relationship. And if it's larger than 0.5, you can say there's a very large relationship. So our correlation here is a 0.57. So I say, hey, there's a very large relationship. But these are just guidelines, right? So I can see you putting a large relationship. So that would work as well. Okay, such that high satisfaction with life tends to be associated with high self-esteem, and low satisfaction with life tends to be associated with low self-esteem. So this is the best way to think of it, and when you're taking the exam this week, you could just use this language and switch things around, right? So basically, what's going to switch would be the variable names, right? And high, low, or very large and positive. So, okay. Oh, so another way of thinking about a positive correlation is this. So as one variable's going up, the other one's going up. As one's going down, the other one's going up. Oh, excuse me, that was a negative correlation. So positive correlation, as one variable's going up, the other one's going up. Negative correlation is as one variable's going down, the other one's going up. Which if you study the scatter plot, that's exactly what you're going to see anyway. Okay, so what I'm going to do now, so this is an example of a positive correlation. I'm going to pretend, okay, that our correlation was negative, and then I'm going to show you what's going to change. I think that's the best way to do this. So in your notes, this is our official answer, right, for our positive correlation. Now we're going to go into hypothetical land. So what if our correlation was a negative 0.57? Well, still, you could say very large or large, whatever you want, though the direction would change. It would now be a negative relationship between satisfaction with life and self-esteem. Now this one, here's how it would change. Remember, as one goes up, the other one goes down. So we're going to have high and low instead of high and high. So such that low satisfaction with life tends to be associated with high self-esteem, and high satisfaction with life tends to be associated with low self-esteem. So that's all that would change there. So go have a good look at that. Okay. So get a mental image of that, because I want to erase it. Okay, I think we're good. I'll go ahead and erase it. Our last topic of discussion today is regression. There are three equations to consider. The first one is y hat equals a plus bx. Oh, by the way, regression is also, you can think of this as we're trying to find the line of best fit. So I think you've probably done that before in junior high or high school. But if not, here we are. Okay. Cool, so we have y hat equals a plus bx, which is the equation of the line. And then we have a equals y bar, or the mean of the y distribution, which in this case would be self-esteem, minus b x bar. Okay, and then the last equation we have is b equals r multiplied by the standard deviation of y divided by the standard deviation of x. Okay, so one really important thing about regression is found in this equation. You see how this y has a hat? Okay. What it's saying is we're predicting, so that hat means predicted y. It means we're predicting values of y from actual values of x. So this is going to matter, right? So if you're told to predict values of self-esteem based on values of satisfaction with life, then you could keep the x and the y like we have them. Okay? Meaning, and it maps on here where we had satisfaction with life on the y-axis and self-esteem on the x. So it's going to matter here when we draw the line. But if you're asked to predict values of self-esteem from values of satisfaction with life, these would actually change, right? Self-esteem would now be on the y-axis, satisfaction with life would now be on the x-axis. So that's one finer point that you should consider. Okay, so now looking at these three equations, which one do we start with? Well, let's see. Well, we can't start here because we need A and B. Let's look at A. Well, we need B to finish A. For B, we just need the correlation and the standard deviation of y and x. Okay. And you know what I did? Silly me. Go back to this graph. I switched them around. That's okay. So what we actually have is our x is satisfaction with life, okay, in our actual problem, and our y is self-esteem. So let me fix that. Was our x. Okay, and then our y was self-esteem. So based on our naming convention, naming y self-esteem and naming x satisfaction with life, we're predicting values of self-esteem, which is y, based on values of x, which is satisfaction with life. Okay, so we're good. We're all mapped on. I'm glad I checked that. We could have gone off in an incorrect direction. Okay, so let's go ahead and solve for B. B equals R. Okay, our correlation is 0.57. And the standard deviation for Y, which is self-esteem, is going to be 0.58. And we know that by going back to our notes, right? Because I gave you the mean, the standard deviation for satisfaction with life and self-esteem a while ago. And our standard deviation for satisfaction with life is going to be 1.32. Okay, we're good. So go ahead and solve for B. So 0.58 divided by 1.32. Then multiply that by 0.57. You're going to get B equals 0.25. Okay. Now that we have now that we have now that we have B, we can solve for A. So A equals, what's the mean for self-esteem? The mean for self-esteem is going to be 3.23, okay, minus B, which is going to be 0.25 multiplied by the mean for satisfaction with life. The mean for satisfaction with life is 4.47. Okay, 3.23 minus 0.25 multiplied by 4.47. So again, following PEMDAS, which is order of operations, you have to parentheses, exponents, multiplication. So you have to multiply this before you subtract, right? So 0.25 multiplied by 4.47. So take that and subtract it from 3.23. So for A, you're going to get 2.11. Okay, so we found A and B. So now we just plug those into y hat and we have our regression equation, or rather our line of best fit. So y hat equals 2.11 plus 0.25x. Okay, I'm going to free up some board space. Okay, so let's do the interpretation. Okay. So we have y hat equals 2.11 plus 0.25x. Okay, our first interpretation is the interpretation for the y-intercept. This is the y-intercept. When x is 0, so plug 0 in for x, 0.25 multiplied by 0 is 0, y hat is 2.11. So all you're doing is you're throwing in 0 there and seeing what the y-intercept is. Okay, the next thing we're doing is we're providing an interpretation for the slope. This is the slope, 0.25x. All we do is we add 1, or we substitute 1 for x. So 0.25 multiplied by 1. For every 1 unit increase in x, right, so put 1 in there, y hat increases 0.25 units. So one thing to note is if your y-intercept, or rather if your slope is negative, so let's say we had a regression equation of y hat equals 2.11 minus 0.25x, then right here, instead of saying increases 0.25 units, it would actually decrease by 0.25 units. Okay, there's one last thing that we need to do. The last thing we need to do is add our line of best fit back to our scatter plot. Obviously, I had to erase the scatter plot a long time ago, but you still have your scatter plot. Okay, so I'm going to estimate what we did, and then I'm going to add the line. So give me a second, I'm going to add it. So that's my estimation of the points that we had. Okay, good enough. Okay. Okay, so to make a line, we need 2 points. So we just need to pick two values of x to plug into the regression equation, right? And then we could say when x is blank, y is predicted to be blank. So we do that twice and it gives us 2 points on our scatter plot. We could then draw a line and label it with our line of best fit equation, or rather our regression equation. So let me show you what that looks like. So point number 1. I'm gonna pick, and you can pick anything, but I picked 0. So y hat equals 2.11 plus 0.25 multiplied by 0. Well, this is easy, right? Okay, goodbye. So when x is 0, y is predicted to be 2.11. So there's my first point for my regression line. Now let's get the second point. For my second point, it looks like I use the mean of x. So point number 2, I picked 4.47. Y hat equals 2.11 plus 0.25 multiplied by 4.47. Okay, so go ahead and solve for that. 0.25 multiplied by 4.47, then add that to 2.11. And you're going to get a y hat of 3.23. So then you can say when x is 4.47, y is 3.23. Okay, so now we can plot those points. So when y is, so when x is 0, y is 2.11. So there's that point. When x is 4.47, which is about here, y is 3.23, which is somewhere about here. So then you draw a line through those 2 points, and then you could add your regression equation, or line of best fit. Y hat equals 2.11 plus 0.25x. Okay, and then that is all that I have for you today. So yeah, you learned a lot more. We were able to take the mean and the standard deviation that we learned from chapter 3 and chapter 4, and we used those to calculate the Z-score. Once we had the Z-scores for the self-esteem distribution, the satisfaction with life distribution, we were able to multiply those together and come up with our correlation. From there, we were able to interpret the relationship between satisfaction with life and self-esteem, and then we were able to also create a scatter plot and our regression equation, or our line of best fit. So good job today. Let's go ahead and pray, and then we'll just close it. Dear Heavenly Father, thank you so much for this day you've given us to live. Lord, thank you for giving us the energy to work hard. I know I'm working hard. I know the students are working super hard to learn this and to apply it to the plan that you have for them, Lord. Thank you so much for being the light in this world. Lord, give us the wisdom to turn to you, to seek you first, to ask you to come into us, to let your light shine through us and transform the world through the calling that you have for us. Dear Heavenly Father, we praise you, we love you, amen. Let me know if you have any questions. Have a great day.